Thank you for the invitation and the opportunity to present our work on hexagonal boron nitride preparation and its catalytic applications. This presentation will focus on hexagonal boron nitride, or hBN, which is a structural analog to graphene with alternating boron and nitrogen arrangements. Its structure is very similar to graphene. hBN lattices are composed of multiple 2D layers held by interaction of mixed with van der Waals forces and ionic bonding. However, hBN is a large bandgap material with an energy bandgap of approximately 6 eV and can be used and be deployed in deep UV emitters. hBN can also be uniquely employed to detect irradiation thanks to its large neutron capture cross-section, especially when it contains B10 elements. Recently, hBN has been considered as catalytic additive materials and catalytic support. Similar to graphene, the structure of hBN can be manipulated to form in-plane heterostructures or stacked heterostructures with other 2D materials. So first, I'm going to talk a little bit about our work using hBN as a platinum catalyst support for catalytic CO oxidations. So in this study, we used hBN nanosheets obtained from gas exfoliation technique. This hBNS is rich in vacancies as indicated by the white squares. When you put the platinum particles, the particles will predominantly go to the vacancy site according to the TEM image. When we evaluate the catalytic performance, platinum supported on hBNS performs better than the platinum supported on TiO2 or silica. It also performs better than platinum supported on bulk hBN. Therefore, we can deduce that the vacancy plays a beneficial role promoting CO oxidation. Theoretically, we build models by placing PD10 cluster on different hBN support. And we also performed the beta charge analysis and found that once the platinum particle is near the nitrogen vacancy, there will be charge being transferred from platinum to the support. Well, for the boron vacancy, the charge transfer direction will be the opposite. Based on DFT calculations, the binding of CO becomes a little bit weaker near the boron vacancy, but slightly stronger near the nitrogen vacancy. We also noted the binding of O2 gets a little bit stronger regardless of the vacancy type. And the stronger O2 binding actually will alleviate CO poisoning and thus promotes the CO oxidation conversion to CO2. It has become clear that in order to apply hBN to various applications, it is important to tailor and improve its synthesis method. Chemical vapor deposition is a popular method to prepare hBN thin films. And copper and nickel are frequently used as substrate because the lattice mismatch is small. Kim in 2011 has reported a micrometer scale hBN monolayer prepared on the copper substrate. In the past few years, we have studied another method called metal flux, using nickel chromium mixture and iron as solvent to dissolve elemental boron and nitrogen elements. And when we cool the flux, so the bulk hBN crystal will be precipitated. And so our group and other groups who have used the metal flux has found that the highest quality bulk hBN can be obtained. So if you're interested, so please follow the following references. So we'll focus on the development of theory and the model here to help us understand the hBN growth. The value of the modeling development is that it enables us to precisely control the growth condition and also allow us to study the molecular mechanism in order to augment experimental investigation. Ultimately, we are able to predict the optimal conditions for hBN growth. According to this workflow, we'll combine the DFT modeling and the molecular dynamic simulations powered by the reactive reacts force field development. We have also developed techniques to estimate the free energies associated with the growth conditions. And also we have some preliminary success in finding new solutions to grow hBN bulk. And all this work has been published in the following references. In our MD simulations, we directly deposit boron and nitrogen elements onto the substrate, and we have developed the force fields for the boron nitrogen nickel system. In order to test whether this force field will work or not, we perform some simulations by putting the boron and nitrogen atoms directly onto the lattice surfaces, and then we monitor the change and the structures on nickel substrate. And we start seeing the formation of a boron nitrogen bond, and they form longer chains. And at the 64 picoseconds, we start to see the first hexagon formed. So this is very encouraging. We let the simulation continue to run, and at 6.25 nanoseconds, actually we start to see a rather complete hBN monolayer network. Encouraged by this development, we start to run a series of MD simulations at different temperatures. So in this set of simulations, we kept using boron nitrogen ratio of 1:1, and our analysis involves the counting of the hexagons. At the 900 Kelvin, we start seeing a number of hexagons, but they are mostly disordered and fragmented. As we increase the temperature, you start to see the number of hexagons increase, and correspondingly, we see larger hBN network. At the 1300 and the 1500 Kelvin, we really start to see the continuous hBN network. And at the highest temperature, 1500 Kelvin, nearly all the boron nitrogen we deposit on the surface have been incorporated into the network monolayer. We contribute the higher temperature to faster diffusion of the element of boron and nitrogen, and also higher temperature helps to rearrange and reorganize these lattice structures in favoring the formation of hexagonal boron nitrogen hexagonal lattice. So these simulation findings can be corroborated qualitatively by experimental results as well. As you can see, different lattice sizes can be obtained at different temperatures. So larger size corresponds to the higher temperature synthesis conditions. We have also performed DFT calculation in order to guide us to predict the shape and the termination of the hBN monolayer domain. So this plot shows the edge energy versus the chemical potential of the element of nitrogen. At the lower chemical potential, hBN domain prefers a triangular shape with a zigzag nitrogen terminated edge. Where on the other end, we also have a triangular shape, but with the boron zigzag edge. In between, we have observed the transition and the preference of a hexagon shape of the hBN domain with alternating boron and nitrogen edge. We test this theory by performing MD simulations using different boron nitrogen ratio. So at the 3:1 ratio, we observed mostly fragmented hBN domain as indicated by the black rectangular boxes. So further growth becomes unlikely as the number of nitrogens deposited on the surface has been already depleted. The excess boron will start forming bond with the nickel substrate and also some boron-based clusters. At the 1:1 ratio, we start to see this triangular domain shape terminated by the zigzag boron edge. As we further lower the boron to nitrogen ratio, the transformation into a hexagon shape domain with alternating nitrogen and boron edges. This allows us to look a little bit deeper into the hBN lattice domain formation. We chose the boron to nitrogen 1-to-1 ratio and at a temperature of 1300 Kelvin. As you can see, we track the trajectory and take snapshots at some significant moments during the simulation. And for the first half of the simulation, it's very uneventful. And the first hexagon didn't start to form until about 5.15 nanoseconds. So once the first hexagon is formed, it quickly grows into multiple joint hexagons. It is noteworthy that so the main growth happens on the sides where there's a lot of dangling bonds and open arms, and so these are the growth frontier. And so in the following few time steps, you can see that that is indeed where the main growth area happens. At the end of the simulation, so we can see the growth basically has completed, and we obtained a triangular hBN domain with the boron zigzag termination. We also investigated the formation of defective structures and the healing of the hBN domain as well. So in one simulation, we actually observed the formation of the pentagon-heptagon dislocation. It turns out this is a metastable structure and quickly evolves into a joined hexagon structure. So it seems like that the formation of some kind of abnormal dislocation is a normal process for the hBN lattice growth. In a separate simulation, we have increased the amount of nitrogen deposited onto the substrate while still running the simulation at the 1300 Kelvin. Initially, the growth process is rather normal, with the formation of the first hexagon quickly evolves into multiple hexagons. In the meantime, at a higher nitrogen deposition ratio, we see multiple domains grow at the same time, and then they can merge into a single domain. In this case, it left behind a rather large vacancy site in the middle. However, this vacancy site also evolves in the next few nanoseconds. And as you can see, it allows the nitrogen and the boron to access the vacancy site and fill this site eventually. We also observe that typically when we increase the nitrogen ratio, the size of the domain becomes larger. And in this case, we can see almost a hexagonal shaped hBN domain with alternating nitrogen and the boron zigzag edges, which is again consistent with the DFT modeling predictions. So finally, I would like to acknowledge my former students Song Liu and Jiahan Li, who have performed the modeling and experimental work. Also my collaborator James Egger and Jeffrey Comer from K-State. My former student Mingxia Zhou has performed DFT modeling on the CO oxidation, along with my collaborator Huiyuan Zhu. Audrey Van Duyn contributed the reactive force field. And also I want to thank various funding agencies to support this work. Thank you.